A 25 milliliter sample of 0.125 molar pyridine is titrated with 0.1 molar HCl. Calculate the pH at each volume of added acid. So this is a weak base strong acid titration. So for A, we can start with finding the moles of each component. So the moles of pyridine is going to be 0.025 liters times the molarity, which is 0.125 moles per liter. This gives us 3.125 times 10 to the negative 3 moles of pyridine. And for the H+, we have 0.1010 liters times 0.100 moles per liter, which gives us 0.001 moles of H+. The reaction that happens during this titration is the pyridine reacts with the H+ to yield the conjugate acid, which is C5H5NH+. So the 3.125 times 10 to the negative 3 moles of pyridine reacts with the 0.001 moles of the H+. So we can subtract the 2 to get 2.125 times 10 to the negative 3 moles of pyridine left. As you can see from the equation, for every mole of H+ added, the same number of moles of the conjugate acid is created. So that means that 0.001 moles of C5H5NH+ is created. We can find the new molarity of each of these by dividing by the total concentration after adding 10 milliliters of acid. So it's going to be 25 milliliters plus 10 milliliters, which is going to be 35 milliliters. So we divide each of these by 0.035 liters to get 0.0607 molar of C5H5N and 0.0286 molar of C5H5NH+. Now we can use our equation pH equals pKa plus log of the concentration of base over the concentration of acid. For this, we need the pKa, but all we know is that the Kb of pyridine is 1.7 times 10 to the negative 9. And we can use our Kw equation to find the Ka. So Kw is 1.0 times 10 to the negative 14th, and that equals Ka times Kb. So Ka equals 5.88 times 10 to the negative 6. So we can plug in our values. We get negative log of Ka plus the log of the base, which is 0.0607, and the acid is 0.286, and we get that the pH is 5.558. For B, we want to find the pH at the equivalence point. So first, we want to find the volume of acid added at the equivalence point. To do this, we can use MaVa equals MB VB. So we have 0.1 molar of acid, and then we have 0.125 molar of base, and 0.2025 liters of base. And this gives us the volume of acid is 0.3125 liters. At the equivalence point, the moles of titrant is the same as the moles of the analyte. So that means that 3.125 times 10 to the negative 3 moles of H+ is added because this is the same number of moles of the pyridine. So if we go back to our equation here, for every mole of H+ added is the same number of moles of conjugate acid is created. So that means that 3.125 times 10 to the negative 3 moles of this acid is created, and we can divide that by the total number of liters, which is going to be 0.03125 plus the original 25 milliliters, which is 0.05625 liters, which gives us 0.0556 molar of the acid. Now this acid is going to react with water to create this equation. it's going to be in equilibrium with H plus and C5H5N. So we know we have 0.0556. Water is not included in our ice table, and we have no H plus or pyridine. So if we're doing an ice table, we can do minus x plus x plus x to get 0.0556 minus x, xx. We know that the Ka is 5.88 times 10 to the negative 6. So our equation is 5.88 times 10 to the negative 6 equals x squared over 0.0556 minus x. For our x is small assumption, we can do 5.88 times 10 to the negative 6 times 0.0556, the square root of that, divided by 0.0556 times 100, and this gives us 0.1, which is less than 5%. So we can assume x is small. So we can just write 5.88 times 10 to the negative 6 times 0.0556 equals x squared. And our x is going to be 5.717 times 10 to the negative 4. And from our ice table, we know that x is the concentration of H+. So we can plug this into our pH equation, which is a negative log of H+, to get negative log of 5.717 times 10 to the negative 4, to get a pH of 3.243. Lastly, for 50 milliliters of acid added, we can follow the same procedure that we did for part A. The new moles of H plus is going to be 0.05 liters times 0.100 moles per liter, which gives us 0.005 moles of H plus. We know that we have 3.125 times 10 to the negative 3 moles of pyridine from part A. And that is going to react with 0.005 moles of the H plus. If we subtract those, we get negative 0.001875 moles. So this number is not possible to have negative moles. It just means that the pyridine is consumed and there are 1.875 times 10 to the negative 3 moles of H plus left over. The presence of this will dominate the pH. So we can just take the 0.001875 moles of H plus that is in excess. We can divide it by the total liters, which is going to be 0.025 plus 0.05, and we get 0.0250 molar H plus. We can plug this into our equation for pH to get negative log of 0.025, and we get our pH is 1.602.